Hello everyone and welcome to the SciRoc camp. My name is Divul Nair and I'll be your host and moderator. Today is the second day of our camp and which is the week-long camp we have planned for you. So the SciRoc camp is basically an effort under the SciRoc project to train new teams to participate in different robotics competition and different benchmarking like basically SciRoc and Robocop and the European Robotics League. So yesterday we had a very good session. We had two teams in the champion stock, Team SciRoc and Team Bitbots. Today, this was very nice in terms of understanding what you call how do teams perform, what are they thinking, how do they participate, and it was really nice to know from the team's perspective. Today we shift on towards the learning side. So today we have our first tutorial, and the tutorial is on robot perception from robotics. Our speaker for today is Mohammad Wasil. Mohammad Wasil did his bachelor's in computer science from University of Trunojoyo, Madura, Indonesia. After which he joined the master's program of autonomous systems, Hochschule Bonn-Rhein-Sieg. He's an active member of the Bitbots team, and as you might yesterday, we got introduced to the Bitbots team for the World Champions. And he contributes towards perception in there. He has participated in different robotics competitions in RoboCup, in Rockin, in RockU2, and the European Robotics League in general. So he's got a good experience with competition and benchmarking. He also contributes to many open source libraries. He was part of the team which won the World Championship in RoboCup 2019, which is the current world champion in the RoboCup at work. He completed his master's in 2019 and his thesis was in geometric deep learning. So as you can see, he has got a good various experience in deep learning, in point cloud processing, using RGB images in robotics in general. So I think it's very good to know what his tutorial will have towards this. So today he's giving the tutorial in the perception for robotics. Now, he was kind enough to provide us with a video. He has recorded it, but so we will watch that. But the format is this way. So currently now we will watch him on the video. We will after the video I'll be joined in live by Basil, and we can ask questions to him from his talk from the tutorial. Also, the tutorial is in a hands-on way. In the end, he goes on with sharing you many of his. It's available in open source, available in GitHub, so anyone can download this and test on their machines. So it's very good for anyone who wants to get it started. Also, it's a hands-on kind of a tutorial. And anyone who wants to ask the questions, please do use the YouTube comment sections. We can have it in there. So that's it from me today. So the stage is set now for Wasil. So Wasil, it's up to you.
Hello everyone, welcome to my presentation on robot perception. I am Mohammad Wasil. I am a research associate at Hochschule Bonn-Rhein-Sieg. My research focus is on robot perception, mainly on 3D robot perception. I have been to several robotic competitions such as RoboCup and European Robotic League since 2017. And in Bitbots, I am an active member, maintainer, and contributor of our open source industrial robotics softwares. I work mostly on robot perception, and now I will present our approach on multimodal object recognition using point clouds and images. In this talk, we will mostly focus on the perception of robot, which mostly operate on industrial environment and smart city environment. Let's first take a look at the environment and the robot. Here, we have a KUKA U-bot, which has a camera mounted on the end effector of the robot, and as you can see on the left side, we have a RoboCup at work environment, which is an industrial environment where the camera faces downward to the workstation. The objects are mostly small in this environment, while in the SciRoc on the right side, the objects are bigger and the camera look forward instead of face down. And there can be decoy or fake objects on the workstation, and those objects have to be avoided by the robot. Let's begin with our perception architecture. In here, we have RGBD camera and OpenAI node on the left side. OpenAI node has access to the camera data, and then from this OpenAI node, the image and point clouds is published to a ROS topic, and then multimodal object recognition node subscribe to that topic using ROS message filter, such that we have the same object from the same timestamp. Since here we have two topics, and thus we need to synchronize them. We start with the point cloud segmentation by separating the points above the table and the table. Once we get the image and the point cloud, we first segment the point clouds to separate the tabletop objects from the table. And we use RunSharks to do this, and this is done via PCL library. Then once we segment the point clouds, we send the image to the 2D object classification node and then send the tabletop clusters to the 3D object recognition node. As you can see here on the right side, we have a 2D object classification node, and in there we have two models, which are SqueezeDat and SSD Lite MobileNet. We perform inference on CPU with SqueezeDat, while we use TPU to infer the image if we use SSD Lite MobileNet. Both models are a single object detection and classification, which output bounding boxes and class probabilities. And then next, to classify the point clouds, we have two different methods. One is a feature-based method, which with SVM and random forest as classifiers. And then we also have a deep learning method using a graph convolution. Once we get the object recognized from two modalities, then we estimate the pose from both modalities. And then we filter out some objects which are out of interest. For example, if we are only interested in on the objects on the tables, then we filter out the objects which are not on the table. And it is useful if we have different environments. For example, if we have a smaller table, then we can also update the region of interest. And this can be dynamically updated via RQT. Then once we get the list from both modalities, we publish them to the object list mergers. And in the object list merger, as the name suggests, it merges the two lists based on some criteria, which I will explain in the later slides. And object list merger node also gets some information from the knowledge base about the facts in the location, what are the objects on the inventory. And then from the object list merger, it publishes a unified object list. You might be wondering why we use two modalities, why we use 3D and 2D. So let's start with some motivation and the problems that we face during the RoboCup at work or SciRoc. So one of the main problems with the image is that it is a 2D representation of an object, while the object itself is in a 3D world. And thus we lose some geometrical properties of the objects. For example, here on left we have a picture of nut. This is actually smaller than the right one. But since the camera position is different, so it seems that the small nut looks bigger on the image plane, while the big nut looks smaller on the image plane. Secondly, deep learning on 2D can be fooled by a picture of the object itself or a fake object. For example, here on the left image, we have two aluminiums. The right aluminium is actually fake. It's just a photograph of the left one. But since they are taken from the 2D camera, they look the same. In most of the time, deep learning on 2D will fail on this situation because they don't have any other properties which can differentiate between the real one and the fake one. On the right image, we have an arbitrary surface, meaning that the background of the table can be different. And this background can be similar to the color of the object. For example, if we have a axis, gray axis in here, and the background is also gray, then we cannot see the object clearly using 2D camera. But on 3D, we will get a point representing the axis. It doesn't matter what the color of the background is. Even though these random or arbitrary surface can be addressed by augmented training, but it is still challenging due to some, for example, similarity between the object and the background, and somehow the camera just cannot see the object. What about 3D representation then? So in this case, it is a point cloud. And then as you can see here on the slide, we have a 3D representation of nuts. The red points represent a big nut taken from farther camera distance, while the blue dots is a small nut, and they are taken from the closer camera distance. If we use 2D, then this small nut will look bigger, as you can see in the previous slide. But in here, it still preserves the critical points of the nuts, points which make this representation a nut, or a big or small nut. So in 3D, it doesn't matter if you vary the camera distance. So the shape of the object or the size of the object will still be the same, even though the density might be different, because the closer one might be more dense, while the farther one it might be more sparse. We can take a look at the 3D plot of these representations. As you can see here, we have the same a small and a big nut. They still represent its original size, and the size is the same as the one in the real world. Nonetheless, deep learning in 3D does come with some challenges. Unlike images, point cloud do not have global parameterization, or there is no common coordinate systems. And it is non-grid-like structure like image. It is just a matrix of pixel, and then it has a variation in the number of points. So meaning that the same object can be represented by a different number of points. And lastly, the point clouds are orderless, meaning that the position of each point can be scrambled, but they can still represent the same object. As you can see here on the slide, we scramble, we move point 0 to the number 4, and then number 4 to the number 3, but they can still represent the same object. So the challenge here is that it is invariant to permutation, meaning that if you multiply this by the weights, different position of the points, they should result in the same object. Let's continue with the point cloud segmentations. On this slide, we have a point cloud which has color, and then a multimodal object recognition node subscribe to that topic, to the point cloud. And then once it gets the point cloud, it filters out the points because we want to reduce the number of points and thus reduce the number of computation. And then we apply SciRoc segmentation, and then once we get the plane equations, we fit a polygon, and then we take the points above that polygon and apply a clustering using Euclidean distance, and each cluster represent one point cloud or one object on the table. So as you can see here on the left image, we have a raw point cloud which has a very dense points. I think it has more than 300,000 points, and then we downsample them. Here on the right side, we have with the red color, and they are more sparse than the original or the raw point clouds. And then after the voxel grid filter, we segment the plane, find the equation using RunSciRoc, and this is done via PCR library. And then we apply a convex hull, and then also compute the polygon, the planar polygon, and then lastly, and we take the points above the polygon and cluster them, and each cluster of the points represents a single object on the table. As you can see here, we have a raw point cloud, and then filtered by a voxel grid filter, and then the red points is a cluster of the objects. Once we get the clusters of the object, we send these clusters to the 3D object recognition node to be recognized. Let's continue with the 3D object recognition node with the point clouds. So we have multiple approaches here. We have a feature-based approaches, and in these feature-based approaches, we combine two features. One feature is coming from radial density distribution, and then the second one is a Fisher factor. And lastly, we have a CNN-based object recognition using dynamic graph convolution. These two different methods come with advantages and disadvantages. For example, feature-based object recognition can be trained faster. So if we have a new challenge and we have a new objects, we can just collect the data set and then train them in less than 10 minutes. While the CNN-based classification method is more robust. However, they are tied to particular objects. So if we have new objects, then we need to retrain them, and then the training will take a lot of time. So during the competition, if we have new challenge, new objects, it is better to use a feature-based object recognition because we can train them faster. Let's begin with the feature-based point cloud feature extraction. We start with radial density distributions. So the idea here is to slice the point clouds along three axes, XY, XZ, and YZ planes. And then for each slice, we fit a circle, and then we divided the circle into 33 bins. So the points which fall into each bins are calculated and then sum. And the sum of this histogram is the feature of each slice. For example, in here on the left we have XY plane slices, and the color represent each slice. While on the right side we have XZ plane slices, and it's the same. The color represents one slice along XZ plane. This method is actually an extension of our approach, which was presented by Santos in 2017, and it was using one plane instead of three planes. Let's take a look at the circle, at the points in the circle. And on left here we have XY plane slices, and then for each slice we fit a circle, like on the right image. So in here, each color in the circle represent one bin or one area, and then we count the number of points which fall into each bin, and then we compute the histogram for each circle. So eventually we have if we have 8 slices, we will have 8 features. Since we have 3 planes, then we would have 8 by 3 features, which is 24 features. Moving on to the Fisher factor feature, it is actually a generative model which is derived from Gaussian mixture model, and it was used to classify images, and this was one of the state of the art before the deep learning era. To make this work on point cloud, so in this paper the GMM is modified, and a set of uniform Gaussians is used, and they are placed in a 3D grid. Like in the picture in here, we have 3 by 3 by 3 Gaussians, so meaning we have 27 Gaussians. And then what are the features? Let's move on to the next slide. So for each Gaussian in here, for each Gaussian, we compute the gradient of the log likelihood with respect to each GMM parameters, and then we normalize them. The features are the sum of the parameters, and the max and the mean of the normalized gradient log likelihood. So what does this normalized gradient likelihood tell us? This gradient describes how parameter of each Gaussian mixture model contributes to the process of generating point clouds. So meaning, if there is no point inside the Gaussian, then it does not contribute, it will be 0. And then let's take a look at the feature representation using Fisher factors. On the left side, we have 27 Gaussians, and then on the right side, we have the features, which is nothing but the gradient of the log likelihood with respect to the GMM parameters. In here, we have 20 by k features. Why not 21? Because we only take the sum with respect to each Gaussian parameter, meaning that we would have the weight of each Gaussians, and then we have the mu and then sigma. And then since it is 3D, they are the weight is 1 and mu is 3, and then the sigma is also 3. We did not take the weight of the Gaussian mixture model because the weight corresponds to the farthest point sampling, meaning that it is always 0. That's why we have 20 by k instead of 21 by k. So what does this feature tells us? For each row, it is actually the parameters of each Gaussian. And as you can see here, the only 3 Gaussians has variation in the number, while the rest are 0, meaning that there is no point in the Gaussians. Once we get the features from both RDD and 3D MFE, we combine them. As you can see here on the picture, we have a point clouds, and then 3D MFE on the top, and then radial density distribution on the bottom. So we have 20 by 27 from 3D MFE, and then 8 by 3 features from radial density distributions. And then we fed them as a input of the random forest classifier. This can actually be trained using deep learning or other methods like SVM. And why we combine them? We did some evaluation on these feature extraction methods using random forest classifier. And as you can see here on the plot, on the very left, we have a radial density distribution. This was tested using our industrial datasets. And then we have a Fisher factor, which has different Gaussian, for example, 2, 3, 4, and 5. 2 meaning that we have 2 by 2 by 2, meaning we have 8 Gaussians. And then we have a combination of the Fisher factor plus the color, because the color is also RGB, meaning we have 3 points, so we treat them as a point as well. And then we have a combination between radial density distribution and Fisher factor plus color. As you can see here, the combination of radial density and Fisher factor plus color has a better accuracy compared to other methods. Let's move on to the point cloud classification using deep learning. In this case, we use a dynamic graph convolution. So how does this work? For every point, we construct a neighborhood and then compute the edges. And then we apply convolution-like, or this is just an MLP, to the edges connecting that point to the neighborhoods. And then for each layer, the graph is updated, and therefore it is called a dynamic graph convolution. It is an end-to-end learning which takes a point cloud as input and then output the class score. However, we made some modification in here. For example, we removed the transformation network because we don't need it. This transformation network is similar to the one in PointNet. This actually transformed the point clouds into a canonical space. Since we normalize the point cloud, we don't need this transformation. And we also found out that it performs similar with and without transformation, but without it is obviously faster without this transformation network. And then we also add color. Instead of just 3D points, we have a 6D points in here to because in our environment we have 2 objects which has the same shape, but they are different in color. Yeah, that's it from the point cloud classifications. Let's move on to the 2D object detection and classification. Let's start with the SqueezeDat. SqueezeDat is the same as YOLO. It's a single stage object detection and classifications, and it uses a convdat to learn the feature map, and it outputs coordinates of the bounding box and the class probabilities for each bounding box. So I'm not gonna explain in detail here what is QuizDat and then how does the network look like. We use this as a 2D object detection and classification node, and we also have a SSD Lite mobile net, which uses a TPU or Google Coral Stick to perform inference. This is actually faster if we do the inference in the TPU instead of CPU. Other than that, we also use Movidius, for example, from Intel to perform inference on the mobile net. Once we get the objects recognized and localized from the 2D object recognition node, we publish them back to a topic, and then the multimodal object recognition node subscribe to that topic. So we only publish the region proposal and the class probability and the label of the object to the multimodal object recognition node. And then let's move on to the object pose estimation and object list merger. This is where we estimate the pose for each object and we transform them to the base link, and then we merge the object list from the two modalities. Let's begin with the pose estimation from a 3D proposals. From 3D proposal here means that it is coming from the 3D object recognition nodes, and we already have a point clouds here, so we don't have to find the points in order to get the 3D position. So we fit a bounding box for each cluster, and then find the pose and the orientation based on this bounding box. And then for the 2D proposal, we take the region which we get from the 2D object classification node, and then for each pixel in the region we find the points. We find the points in the 3D world. Then once we get the cluster of the 3D points, first we apply some filter to remove the outliers. For example, remove the plane from the objects, and then we use PCA to find the orientation of the object. So the pose is always at the center of the object, except for some complexly shaped objects, for example axis and bolt, in which we calculate the pose at the center of the gravity, such that we can have a successful pick for the robot. Moving on to the object list merger. Here, object list merger gets two lists. One is from the 3D proposals, and then second is from the 2D proposals. As you can see here, the white ones are coming from the 3D proposals, and then the green ones are coming from the 2D. And how do we merge them? So we merge them based on the following criteria. So we have information about what objects are on the table. So this information is coming from the knowledge base, which we get from the central factory hub. And then we also consider the class probabilities from both modalities, so which is higher and which is better. And then we also have a prior knowledge about the accuracy for each model and for each specific object. For example, if it is about color, if the model confuses about the color, then we prefer to take RGB, because RGB is always better in color. But if the problem is in the shape, then we take point clouds. We take the proposal from the 3D instead of 2D. So we combine this thing in the object list mergers, and then publish a unified object list to a topic, and then object selector node subscribe to that topic. So in this object selector node, it does nothing but select the objects based on some criteria. For example, the closest to the robot base, and also we can also pick the objects based alphabetically. And then once the object is selected, and it publishes this to again rows topic, and then perceive action subscribe to this topic. Yeah, that's it for the theoretical part and the architecture. So to make this presentation less boring, let's do some demo. We will use our Docker image to do some demo, and you don't need to install, if you want to follow this, you don't need to install full ROS. You just need rfis and rqt, and that's it. You can run our Docker image, and then run our perception in the Docker image, and then open rfis in your local PC. Yeah, let's start the demo. First, let's go to our Docker repository and then clone this repository. If you go to the industrial, there is a tutorial on how to use this Docker image, and clone this to your local PC. Since I already cloned it, so I don't need to reclone this. Then if you go to industrial, you should have these files. And then next we need to pull our Bitbox industrial image from the Docker Hub. This is under Bitbox industrial. The tag is kinetic base, and this will pull the kinetic environment. So this will take some time. Let's just skip it. Once we get the image pulled from the Docker Hub, then we need to pull our unmerged perception packages, which we want to run locally in our PC. So if you go to my repository, embed Wasil mass industrial robotics, change the branch to unmerged perception. And then clone this and specify the branch. Since I already cloned in this PC, so I already have mass industrial robotics. But first, let's check the branch. Yeah, we are in the unmerged perception. Then copy the path of this. And then go back to the Docker Hub. And then in the start container.yaml, and then under volumes, ROS kinetic container, add that volumes. So there is an instruction here on how to mount your local packages to the container. So we provided an external mounts in here, and this is owned by RoboCap so that you can read and write, and these changes will reflect your local changes as well. Let's just copy paste this, and then this will be mounted to RoboCap kinetic external mounts, and the permission is read and write. And that's it. Let's bring the container up first by docker compose, and then the file start container.yaml up, and then the name of the container, ROS kinetic container. Now check if the container is running. So just copy paste the name of the container. Then just log in to the container by docker x, and then the name of the container. So now we are in the container. So we will have mass industrial robotics. Just remove or catkin ignore this one, because we already have this in the external mounts. This is our local package. In here, let's just remove this mass industrial robotics. When it is removed, let's just build this. Catkin build main object recognition. The name of the package is mere object recognition, and this will take some time. Once it is done, source devel setup.bash, then we can check what object recognition model we used. First we can check the RGB. So in the RGB we use a squeeze that classifier, and the data set is at work Sydney. And then for the 3D, ROSET mere object recognition, point cloud object recognition node. And then here we have the model is CNN based, and then the model ID is CNN, dataset it has. Then we need to launch ROScore in another terminal, just to make sure that it doesn't get killed when we kill the ROS launch. This ROScore is running locally in my PC, and this, as you can see here, this is Noetic. Then now we can launch the multimodal object recognition node. So this multimodal object recognition node is running in the container using Kinetic. First, let's launch the back file. Because I already recorded the point cloud and image data, you can download this from this link. Back, play, and then the name of the back file. So once you get the back file running, now you can check RFIS. So here, check the raw image, and then we can also check the raw point cloud. So now check the topic. So now we have these topics, and this is the topic from the camera. This is point clouds and the image, and then we need to trigger the multimodal object recognition to event10 by sending e-start to the event10. Then it will start recognizing the image and the point clouds, as you can see here. So we have, on the left we have the RGB from the squeeze dat. So it detected 3 objects, and so we get a correct classification result in here. And on the right side we have the point clouds. It says decoys because they are out of region of interest. Later I will explain on how to extend the region of interest. The white color come from the 3D, while the green one come from 2D. Let's just remove the 3D. And yeah, these are they come from RGB. Let's go back to the terminal. Let's see what's happening. So what's happening here is that multimodal object recognition get triggers and then subscribe to the point cloud and image using ROS message filter. Start segmentation, and then publish the cluster to the 3D object recognition, and the image, the 2D image, to the 2D image recognition, and then wait until it gets recognized. Once both get recognized, then filter them and then remove the objects that are out of region of interest. We have 2 objects from point clouds here because the camera cannot see the small nut, and we get 3 from RGB. So now let's fix the region of interest. So we need to update the ROI configuration by running rosrun rqt reconfigure. If you run this, you will see a lot of parameters here. So the first one is the parameter to adjust the object height on the plane, and then the second one is the point cloud segmentation parameters, like the cluster minimum size, cluster maximum size, and then pass-through filter, and then this is segmentation parameters, and then we have a voxel filter parameters here. We can also increase the voxel leaf size. Then we have a configuration of RGB proposal. If you want to adjust the bounding box proposal from RGB, like if you want to increase the bounding box. And then last one, we have a region of interest parameters. So the second one is here is the ROI, the maximum object post X to the base link, which is the distance of the object to the base link. If it is out of this area, then it will be filtered. So let's just increase this to 1 meter. Then retrigger the node and send e start again to the event in, and then now it should not get filtered. So the proposal from RGB and 3D are correct, except that the 3D cannot see the M20 because the camera cannot see M20. Let's see what happens if we change the classifier. Let's change the feature based. So we want to change the model based to feature based, and then the feature, the model ID, which is feature factor and radial density distribution, and the dataset is access, and then relaunch the node. So once it is running, let's trigger this again. First, let's clear our face and then retrigger. So now the 3D gives container box red here, which is misclassified. So actually S4040G is classified as container box red, but the proposal from the classification from 2D is correct, S4040G. So that's it for the demo. I hope you are enjoying the demo, and we do have some future works, and because we still have some open problems. So we want to make the model run on edge devices, on TPU, or some faster inference, or some edge devices which can perform faster inference. And we want to improve our pose estimation. Maybe a more generalized pose estimation is preferable, and we want to do continuous deployment such that we don't have to worry about the continuous integration, delivery, and then continuous deployment to the robot. And we want to make these components in the robot perception more modular, and we want to run this in microservices and use something like Kubernetes or Docker Swarm to manage them, such that we don't have this single point failure, because currently it is running on its own. So if the node fails, then there is no one who will take care of this. So somebody has to come and then rerun the node. That's it from the robot perception multimodal object recognition using point clouds and images. And thank you for your attention. If you have some question, please ask in the comments, or you can also raise some issue on our GitHub repository, github.com bitbots mass industrial robotics, or you can also read our documentation in the bitbots.read the docs. And thank you and stay healthy.
So thank you for the demo, Wasil. I think thank you for the tutorial. It was really nice. What I really liked was this configuration-based setup. So as I promised to everyone, we have been joined live by Wasil. So please welcome Wasil. Hi, hi
Hi,
Wasil.
Dibul.
How are you?
I'm good, thank you. How are you, Dibul?
Good. Thank you. I'm also good. And welcome to the SciRoc camp. And first of all, let me thank you for giving this informative tutorial. It was really nice. I think any new team, and with even with the demo and the code, I think any new team who wants to start,
Yes.
I think they can start at a place where you are. So for the audience, if you want to ask any questions, do use the YouTube comments to ask any questions. In the meantime, when the questions are coming, let me ask something which I found it very intriguing. So one thing you said was the process for data collection, right? So you mentioned it is so you suggest us to do feature based for
Right.
computations because it's not data intensive, but still you need data, right? So how is the data collection process for the point cloud? Let's say we'll begin with that.
Yeah, that's interesting question. So we have an automatic data set collections. So we put the objects on top of a table, and then we also use 3D in that case so that we can replace the background later on for augmentation. So that is easy to collect like bunch of data in, in 1 hour, then we don't have to label them because this is automated. This is also open source software, and this is done by some students in MAS and also some R&D students.
So this is available also on the
Yes,
Bitbox.
yes.
Nice. That's all okay. And so do you think the data set you have collected, so does it need to be redone in the robot place? So do we need to recollect the data set? So it's easy to collect. So
Yes.
even
In every competition, we always collected the data sets because, deep learning somehow fails, does not generalize well in different environment.
okay.
And therefore, we kind of fine tune the model and then we collect the data set that would make the model better.
Even for the point clouds, you're saying.
Even for the point clouds, it is the
Okay.
same because
Because I was
in
under
this
the
case,
perception that okay, maybe point clouds you don't need it is the same
yes,
in.
but since we use color, somehow
All
like
right.
it's like we have gray object,
Now,
you have a
yeah.
different lighting condition. It might look white on the
Now it makes
camera,
sense.
so that's
Yeah.
one of the problem.
Nice. So the other question which I was wondering is, so what are the failures? What are the limitation of your feature-based thing? Because and it's very intriguing to know that in this deep learning process, there are teams who are still using the non-deep
Mm-hmm.
learning thing. So what are the failures? What do you think have you faced any limitations? What are the limitations of this method?
Well, in general, since we only look once and then pick or whatever transfer the objects, so it's not really an active perception where we cannot track the position, we cannot re-estimate the pose while the robot is trying to pick. Let's say there is a movement on the objects, then we cannot realize that, the robot cannot realize that. But if we
Right.
switch to an active perception, maybe that could help because we always re-estimate the pose of the object as well as the label. That could also help the model to understand, to get more features of the objects because the camera is getting closer and the density might be better and the color might also be better.
So you're saying that you want to move away from this process because what I understand is that you perceive and then you have a pose once and then that is which is given to the manipulation and you want to build on this because this is a limitation of the current process choosing.
Yeah, a closed loop perception and manipulation might be better
Right,
in this case. And
right,
yeah, we that is one of our future works.
right, right.
Yeah.
So in your slides, you had a very brief thing about so talking about what do you call the since you have this two, right, the feature based and then the
Exactly.
CNN. So and then you had talked about how you combine things. So what if there
Mm-hmm.
is a conflict? So so you showed in the demo also that we saw there is a conflict coming
Mm-hmm.
from
Mm-hmm.
the point cloud. So who is the one who makes the decision in there,
Yeah,
and what
that
is
is
it?
that is interesting question. So we have an object list merger here, which merge these two result from these two modalities. So we have some information, for example, an object at the location which we get from the referee box. We get that is the facts that those objects are available on the table.
Yep.
And then we also put something like knowledge, something like we have a rule base. So for example, we know that point cloud works, point cloud is worse on recognizing the color of the object, but then we prefer, if they are confused about this, we prefer RGB. On the other hand, if we have a confusion between the shape, for example, small net or big net, then we prefer point cloud because point cloud works better in that situation.
So you have set of rules
Some sort
which
of rule in the object list
okay,
mergers. So this
okay,
is like
okay.
a human rule. We know that this also, we also have a prior knowledge about the model, like model. Is this model working better on these data sets? Or the 3D is better on that data set. So we have that kind of information.
So what do you think in the future is there? So currently, if I go around, all the robot perception has been taken over by deep learning, right? So
Mm-hmm.
and now I come to your team and you're following the point cloud and processing based methodologies. So
Well,
what do you think in the future is? Do you think there is still hope for doing the basic without deep learning based methods in the?
yes, of course, there is at some point feature-based classical method is better. Like for example, in object detection,
Yeah.
if we have a new objects
Yes.
and you cannot segment, your deep learning is totally doesn't work. It
Yeah.
doesn't work in the situation where the object is
So
new.
this
You
is the
cannot segment
scalability
them.
part of it.
Yeah, the
So
scalability.
yeah.
And but if you use feature or some classical method, you can still use it.
I
Maybe
think
it perform worse on some situation, but it will work.
yeah, I think the right word is not scalability. It is the time to change. You know the to modify yourself. So it is so the deep learning is so you cannot change it on your will. You know you have to collect
Exactly.
data. So you have to. It's a long process.
Yeah.
While on
Not,
the
not
feature processing, it is.
not to mention the time to train.
Yeah.
That's a big problem. Yeah, yeah. Like during the competition,
So
you have
what is your
something new.
time? What are your times? How do you train and what how much
Well,
time does it take?
well, for the squeeze dead or other point clouds like point net or DGSN, it takes like, I know it depends on the data set too, but it was mostly like 10 hours. So,
Wow.
but you cannot do this in competition. You have
Competition,
a
yeah, yeah,
new
because yeah.
setup, new objects, then you have to prefer the feature base. That's the solution.
Okay, nice.
Yeah.
Now to talk to consumer, what about the computation power? So I know we saw the U-bot in there.
Mm-hmm.
So we had your team presenting, and they had shown a bit about the hardware. Where we had it's a Nook, which we know from the presentation yesterday. So how much processing power is required by, let's say, by the processing, by the feature based, by the DNNs, and yeah.
So in total, it just takes uh, it gives us 2 frames per second, 2 hertz. The whole perception, 3D, including the segmentation, RGB, the whole perception pipeline, it takes uh, 2 frames per second or 2 hertz. But this can be improved by using a Coral stick or a TPU or some
Okay.
other edge computing.
Right.
So yeah, we are like working on that to make the point cloud feature for point cloud models to work on the edge TPU or edge computing as well.
And finally, so I saw you using Docker in your demo, which was very nice to set it up. So So is this the standard perception way of deploying
Well,
this?
it's not really standard in the sense because the communication between the host and the Docker, it takes a lot of time.
Okay.
You already have ROS topic with the networking as well. So if you communicate between the host and the Docker, it might take some time, but it might get improved. The advantages here is that if we have a Docker base, then we don't have to worry about the environment. You can deploy
Yep.
this on any platform because it's
Okay.
just running on its own image.
Good. Good. I think we have discussed a lot aspects of it, and I wish the whole bigger robotics community can learn from the experiences and this tutorial of Wasil. With this note, I would like to thank again Wasil for joining us today
Yeah.
and
Thank you,
giving us
Dimple.
this tutorial. And see you soon in the next competition. So as you know, we are having the next SciRoc competition in Bologna, Italy, and then we hope to see you there.
Yeah. See you. Ciao, ciao.
Bye bye. Okay, so that was Wasil and the tutorial, robot perception tutorial. So before we leave, I would like to share you what do we have for tomorrow. So not to forget, uh, just a second. Yes. So that's what how it looks for the week. So we are right here today on Tuesday for perception tutorial, and the whole week we have our the whole week we have uh, the whole we have the symposium running around, and on so what is there what tomorrow we will be joined by Oscar Lima, and he's giving us a tutorial in robot task planning. So all those were questions around, how does the planning in robotics work. I think it's a good place to start tomorrow. It's from 14 to 15. Uh, so be prepared. And finally, let me thank my team members who are helping me in there. So it's Iman, Santosh, even Miriam, and the whole marketing department, Kira. Also, our sponsors, BIT and the international department in here. So thank you, everyone. And this is Dibul signing off for today. Bye-bye. Ciao.